All right, guys. In this clip, we would like to review Rolle theorem and also apply it, if applicable, to a couple of examples I prepared. All right, Rolle theorem has three conditions. Okay, first, it has to be continuous on a closed interval. And secondly, it must be differentiable on an open interval. Thirdly, the function's value at the endpoints must be the same. If all three conditions are satisfied, then there exists a number in the open interval such that the derivative of the function at this point is equal to 0. So let's look at the first example. It should be pretty straightforward. It's a polynomial. And polynomial is continuous indefinitely in its all real numbers in its domain, which is all real numbers, and differentiable everywhere for infinite number of times. And so differentiable, all satisfied, and we check the value at endpoints, they are the same. We just plug in the numbers. And therefore, we found the derivative according to Rolle theorem. Okay, so by Rolle theorem, there exists a number C inside the interval from -1 to +3 inclusive, such that the derivative of the function at C is 0. That means replace x by c. That's 4c minus 4 equal to 0. So solving this equation for c, we got c equals to 1. So c is the number. Obviously, c is inside this interval, and c, the number found. Okay, the number is found. So that was done. Example number 2 is a trig function related. It's a trig function related. So, well, trig function is a continuous differentiable indefinitely in its domain. So the continuity is satisfied, no problem. At the endpoint, the function's value at pi/2, we plug in sine of pi/2 divided by 2 is sine of pi/4, that's √2/2. Sine of 3pi/2 divided by 2, that's sine of 3pi/4, that's also √2/2. So these two values are the same. So all three conditions are satisfied. Okay, all three conditions are satisfied. And then Rolle theorem applies. Then we say there exists a C such that the derivative of the function at C is equal to 0. And I found the derivative from the start. Okay, you can either do it at the beginning or you can do it somewhere in the middle when we need it. So we ended up solving this equation, for C. So we came to this point. So what do we like? See this equation is as cosine omega equals to 0. So what are those values that will make cosine omega equal to 0? Just solve this equation in general. Well, that omega needs to be what? That omega, we know cosine pi/2 equals 0, right? So that omega would be equal to pi/2. Pi/2. 3pi/2. 3pi/2. Okay, in fact, we have -pi/2 also works, -3pi, will also work, and there are many such solutions. But remember, we're only looking for solutions that's in this interval, right? But that's for omega. And what is omega? C/2 is omega. Okay, so really is C/2 is equal to cosine c over 2 is equal to 0, right? So we can forget about this. We just think of it this way. If c over 2 equals to plus minus pi over 2 plus minus 3 pi over 2, what does c equal to? What does c equal to? Right? You would multiply both sides by 2. That's going to be plus minus pi plus minus 3 pi, right? And we can keep going. However, the c we are looking for is inside this interval, right? So what c is really relevant to us? The c that's really relevant to us is pi. It's really pi. And only this number is inside this interval. So applying our knowledge about trig function, but you also need to know the kind of c we're looking for has to be within the specified interval. So within the specified interval, we really just have one. So some of these parts you may like to do it in on scratch paper, okay? And so we have only one value c, right? So you may go back there. Just if you write it this way, it will be fine. So in terms of showing your work on this part, what I just wrote down should be put on scratch paper. In your work, you just show this, you show that. Okay? Now let's look at the third question. Okay? I'm going to bring this theorem under. Okay, so here's the theorem for our reference. And you probably have it in your index card. And this question, we have a closed interval. So once again, we're going to check the conditions. And the domain of this function is not all real numbers. Is x cannot be 0. However, the interval of our interest does not include 0, right? So we don't have any problem about continuity and differentiability in the given interval. All right, so let's begin. The solution. Okay, so first of all, the function is continuous. The function is continuous on the interval closed. Secondly, the function is differentiable inside the interval, inside the open interval. And thirdly, we need to check the condition. We need to check the condition at the endpoints. So we take this function. Okay, we're going to evaluate this function at a point half. Okay, so x will be replaced by half. X replaced by half. And the second one, x is replaced by 2. And let's see what we got. On this one, we got half plus 2. which they're the same. You can see they're the same. We don't need to evaluate further, right? So f of half is equal to f of 2, right? So by this time, all three conditions are verified and they are satisfied. So we can go ahead, right? So you can say by Rolle's theorem, there exists, right? So there exists. So we really just copy these sentences and put put a specific function in place, right? There exists a C inside the interval, and the interval we have is from half to 2, such that this is true. We haven't found the derivative yet, right? So let's find the derivative. So f prime of x, the derivative of x equals to 1. The derivative of 1 over x is negative 1 over x squared. Okay, so f prime of c would just be 1 minus c squared under 1 equals 0. So we're solving this equation for c. We're solving this equation for c. Let's see what we got. Let's see what we got. All right, from this equation, we got 1 equals to 1 over c squared. 1 over c squared. All right, and that means c squared is equals to 1. And of course, we're going to take square root on both sides. We're going to take square root on both sides. The square root of 1 is 1, same. And we got the absolute value of c, which is equals to 1. And finally, we got c equals to positive 1 or negative 1. But negative 1 is not inside the interval, right? C equals to, we can say negative 1 is not inside the specified interval. So we're going to drop that. 1 is in. So C equals to 1 is in the interval of our consideration. So that we found the C. All right, last one. Okay, last one. Example number 4. In this question, we are, and of course, and this is how it's being phrased. Okay, so take a look. We have a function called tangent x, show that f of 0 equals f of pi, but there's no number c inside this interval such that the derivative of the function equals 0. Why does this not contradict Rolle's theorem? Okay. Well, first of all, let's check all three conditions. Okay. The function, which is tangent x, its derivative, right? Its derivative is secant squared. Right? If we go ahead without checking the condition, then we may, because we know f of 0 equals to f of pi, which is true, right? F of 0 f of 0, tangent 0, indeed is equal to 0. F of pi indeed is equals to tangent pi, right? Tangent pi equals sine pi over. If you're not familiar with these numbers, tangent pi equals sine pi over cosine pi. Cosine pi is -1 and sine pi is 0. 0 divided, cosine pi is -1, so it's going to be 0, right? So for those of you who are familiar with trigonometry, you know this is true. Okay. And if you go ahead, say, oh, I'm going to apply Rolle's theorem. I'm going to take the derivative, right? I'm going to take the derivative, which is f prime of c and equals to 0. Well, what do we get? Right? What do we find a solution? Well, secant squared c is equals to 1 over cosine square of c. That equals to 0. Numerator is 1. Denominator cannot be 0. Denominator can never be 0. So there's no solution. Indeed, okay? The statement in the question is correct. No solution to C. Such C does not exist. Such C does not exist. The question is that this contradicts with Rolle's theorem, right? So we just basically illustrated what the statement in the theorem says, which they're all true. Well, why does this not contradict with Rolle's theorem? Well, let's look at continuity. Okay, why? Then we say this does not contradict to Rolle's theorem, because if we cannot find the C, there must be something is not satisfied here. The third condition is satisfied. So we just have to check the first or second, right? Is the function continuous? Okay. Is the function continuous? This function is not continuous on the closed interval 0 pi. Why? Because between 0 and pi, since the function f equals to tangent x is not defined at pi over 2. Pi over 2 is a number inside the interval, okay? Therefore, it is what the first condition is not satisfied. And if it is not continuous in that interval, certainly it's not differentiable in that interval, right? So actually, two conditions are not satisfied. So first one, f is not continuous on that interval because f of x is not defined. If it's not defined, it's not continuous. It's not continuous, it's not differentiable. Do we need to mention it is not differentiable? You could, as a result, right? F is not differentiable. At pi over 2. So all that logical relationship we talked about before, and if it is not differentiable at a point in the interval, then f of x is not differentiable in that interval. Okay, if it's not differentiable in a point in the interval, then it is not differentiable in the interval of 0 pi, because to be differentiable on an interval, the function has to be differentiable at every point in the interval. All right, so if not all the conditions are satisfied in Rolle's theorem, there's no guarantee of the conclusion. And therefore, this does not contradict to the Rolle's theorem. And that's all for this lesson. Thank you so much. Thank you.